Hi, everyone. So today we'll bring you a session about real-time machine learning features for payment fraud and what we learned from shipping them at checkout.com. And we have billion event scale. So yeah, quick round of introductions. I'm Dinis. I'm a machine learning engineer at Checkout. I work at the intersection of machine learning systems for fraud and our machine learning platform. And I'm together with Matt from Databricks, which specializes in low latency streaming pipelines at scale and has been working with us for the last 6 months. Before getting into the session, I want to present what Checkout does. So basically, we are the payments infrastructure for some of the largest brands in the world, some of which you might be familiar with, like eBay, Uber, and Spotify. And basically, we try to solve some of the common challenges that you have in payments, such as improving acceptance rates, which basically means ensuring that the payments are accepted, but also trying to prevent fraud for our merchants, trying to protect our merchants and their customers. We processed over 9 billion payments last year, which amounts to $300 billion, and we've seen across our network over 1 billion cards, so you get an idea of the scale at which we operate. For every single payment that we process, we run the payment through multiple machine learning models. Some of them are used to assess the risk of the models, the risk of the payment, so basically like whether the payment is fraud or not, and this is going to be the focus for today's session. Okay, so payment fraud happens really, really quickly. Some of our merchants are constantly targeted by fraud attacks, and during an attack, they can have thousands of payments every single second. And for each one of those payments, we have to decide in a 100 to 200 milliseconds window what to do with that payment, whether to block it or not in case we think it's fraud. If we get the decision right, we are able to flag over $100 million every single year in fraud. And for this, we need to build real-time machine learning features so that our models can use to detect this type of attacks. And this type of features is what we are going to focus on today. Let's go over an example of a fraud attack. Obviously, this is not a real example, just to show how it works and some of the things that we see in our day-to-day. So it's 2 a.m., and a fraudster has a bunch of cards, stolen cards, and a script. The first step is basically to run those cards over smaller merchants with just tiny charges to see which cards work versus the cards that don't. And the second step is taking the cards that actually work and run them through bigger merchants and try to buy anything that is resellable. For a machine learning model for fraud, what's really useful in this case is how many cards we are seeing from this fraudster based on the IP that they are using. And obviously, for every single payment, we have to decide really, really quickly what to do with this feature. And we can't really run a query on a database that tells us how many cards were used for a given IP, because we only have 100 milliseconds to decide whether to do this, whether to block the payment or not. And we use hundreds of features in our machine learning models. So you can see in the chart on the right that one option to do this is to run jobs in the background that keep updating those features. And the top row is if we add a Databricks batch job running every hour. And you can see that it wouldn't be really that useful because throughout the entire attack, the feature value would have been 0. And instead, what would be really useful for the model was basically to refresh that feature value every second or every few seconds. And this is what we can achieve with real-time features or a streaming job running on Databricks. We already had a feature store at Checkout, and it was actually we had a lot of features, and we were covering a lot of scale. So we had over 500 feature definitions, 5 billion feature values being served. We have extremely high throughput because we see a lot of payments, and for each payment, we might look up multiple features. So we had over 1,000 KPS, and the latency was there as well. It was extremely quick. Basically, every single lookup is a key value lookup, which happens in under 10 milliseconds. So this shows that serving the features was not necessarily our bottleneck. Our bottleneck was computing them upstream and making sure that they are fresh enough so that we can identify the fraud attacks that we were seeing earlier. So shipping real-time features is actually 2 problems. I think freshness is the first one that always comes to mind, basically how fresh the features actually are. The second one, which is actually what most teams forget, is that the features that we are serving in production need to match exactly what the model was seeing when we trained the model. And we actually decided to focus on parity first. And we went for sliding windows, which almost give us parity for free, while we know that there's only so much that we can do in terms of freshness with sliding windows. But this was our first approach to try to deliver value with real-time features in production. Let's go over the end-to-end process of shipping a new feature with sliding windows. So basically, a data scientist comes up with an idea, and we can use the same example as before, which is the distinct cards that we've seen for a given IP in the last 5 minutes. Then we created some sort of like DSL that they can use to define the feature. So they use a decorator feature job, they write a Python function, and in that Python function, they need to provide what's the source of events that they are going to use for the feature. In this case, it's a Kafka topic with payment events. Then what's the entity that we are aggregating values for, which is the customer IP. The type of window that we are using, which is a sliding window with size 5 minutes that slides every 30 seconds. And then the aggregations or features that we want to compute within those windows, which in this case would be just the count distinct of cards that we've seen for this IP. After the feature definition, they can run a bunch of research. So they backfill the historical values point in time. They attach a notebook, run a few experiments training a model, evaluating the model, and trying to iterate to find which features are best for the model. Once they are happy with a feature, they can ship the feature to production, and we automatically provision all the infrastructure that they need, and we actually provision 3 pipelines for them in production, which we will see next. Provisioning the infrastructure is actually done with Databricks asset bundles, so everything is automated, and the only thing that they have to do is to write a bunch of Python code, and we get the infrastructure automatically provisioned for them. The 3 pipelines that we provision for the data scientists are, so the first one is where everything starts, training a model. So we have a pipeline that keeps computing every single day the point-in-time correct values for the features that they just defined. Then we have a pipeline for serving, which is basically what's going to keep updating the values once we take the model to production. And the last one is a pipeline to make sure that the features that the model was trained with are also the same features that the model is now seeing once taken to production. Let's focus and deep dive into the training pipeline, or rather the pipeline that is used for the training features. So basically, the most important thing in the offline feature computation, as we call it, is to make sure that the feature definition that the data scientist wrote is going to match what we have in the offline feature computation. So basically, that the features are computed with point-in-time correct values that they can use to train their models. So for instance, like for a payment that happened at 2:14, our offline feature computation job needs to ensure that the feature value that we have for this payment is the same that the online feature computation pipeline would share with the model when we run inference in production. This is the end-to-end architecture of the offline feature computation. So basically, it all starts with a source of events. In this case, we have an event source as a delta table with historical payment events. And then we have a feature engineering pipeline which runs in batch every single day. It's basically like a Databricks workflow. And then we use the feature engineering client provided by Databricks to create an offline feature table in the feature store. So it's also a delta table with historical feature data. It belongs to the Unity catalog, and it's automatically registered in the feature store as well. What this means is that then consumers can attach their notebooks to a cluster and read the features from the feature store and use this to do their research. Or our production training pipelines can apply the same approach to get the features from the feature store and do model retraining automatically. Once we have the offline features in the feature store, training a model becomes really easy thanks to the tooling provided by Databricks as well. So we use their client to provide it like a data frame of payment events and a label, which in this case is whether the payment is fraud or not. We create a feature lookup based on the feature tables that we have in the offline feature store, and we are able to create a training data set based on this. After creating the training data set, we can just train a model, and once we are happy with the result, we promote the model to the model registry, and we are ready to serve the model. So now that we cover the training part and we have a model ready to deploy, we need to focus on the serving part. So basically, now we need features that the model is going to see in production, and we can use those features to decide whether the payment is fraudulent or not. And while for training, we need historical features to train the model, for inference, we just need the latest feature values. So for instance, for the fraudster IP, we only need to know how many cards they used in the last 5 minutes. In production, we use sliding windows. So basically, as you can see in the chart, every row in the diagram is basically like a new window, which spans over the time of like 5 minutes. And every 30 seconds, we slide the window. So we end up with a new window. As soon as we get new events, which are the dots in the diagram, they fit basically the window that is open at a given moment in time. So you can see that in the first window, the count would be, or the number of events in the window is 2, while in the last one is actually 5. And we do this for every single entity that basically has an open window. So we see a lot of, due to our scale, we see millions of IPs in a short amount of time. So what we see is actually like millions of entities, different entities, times the amount of windows that we can have open in a given moment in time, which in this case is 10. The reason why it's 10 is because basically like in 5 minutes divided by 30 seconds, we get 10 active windows. Two things that are also worth mentioning here is that we always keep a watermark to account for late events. And every time a window closes, we write the feature value into our feature store. So this is basically translated into a new feature in our feature store. This is how the end-to-end feature computation works for online. So it all starts again with an event stream. But in this case, instead of a delta table with historical events, we need what's happening in a given moment in time, what's happening right now. So for that, we consume the events from a Kafka topic. And then we have the feature engineering pipeline running as a Spark declarative pipeline, computing the sliding windows. And we use RocksDB as a state store as well. And finally, we write this into an online feature table in Delta. Because Delta is not appropriate for inference, because we can't really do single-digit lookups in Delta, we have a downstream pipeline which consumes from a streaming Delta table, takes the features, and publishes it to a DynamoDB table. This is actually that we are working on replacing. We want the feature engineering pipeline to write directly to Dynamo so that we don't have the step in the middle, which is adding a bit of, where we are losing a bit of freshness. Okay, so we now have a training pipeline, we have a serving pipeline. The only thing left to cover is a monitoring pipeline to make sure that the two are providing the same results. When it comes to monitoring, we basically focus on two different things. The first one is parity, to make sure that what the model is seeing is the same thing in production, is the same thing that the model was trained with. And if it's not, you can see in the chart below on the left side, it's basically like we expect most payments to have the same features in production and in the training data set, and we do this through feature logging. So basically, like for every single payment that happens, we log the features that were used for that payment, and then we compute the same payment in our training data sets, and we check whether the features match or not. And you can see that if the match percentage starts decreasing over time, we know that there is a bug, there's skew between training and serving, and we need to create an incident because probably there's something wrong with the model. The model is not being used for what it was trained to do. And then we can also have drift, which is, it has nothing to do with training serving skew, but the distribution of the features themselves are changing. So for instance, for the feature that we are talking about distinct cards used by an IP in the last 5 minutes, we can have an average of like 5, and then out of nowhere, we see that the value is the average is increasing to 20 or 30. And in that case, it means that there's something in the world that is changing, and our models probably need to be retrained because they are not accounting for the new fraud patterns that we might have in production right now. Okay, so what did we learn from taking all of this to production? So the first one is the reason why we picked Parity in the first place. So essentially, we had data scientists creating their own backfill logic to backfill the features. And in this case, they were, for instance, counting the number of declines for a customer in the last 5 minutes. And they were interested in the charge request that happens at time t. And you can see that there's actually like 3 payments that happened before that time that were declined. So everything sounds fine, right? Well, actually not. A decline might happen a few seconds or even minutes after the payment was requested. And in this case, actually, like only one of those 3 payments was declined before the charge request at time t happened. So we had leakage because the model was accessing a decline event that only happened after the payment that we are taking into account. So in this case, the real value should be 1 instead of 3. And the model was learning from something that we wouldn't have access to in production. With the new decorator that we created, basically the training and serving pipelines are set up automatically, and we ensure that there's no leakage because we always monitor the training and serving skew, and the features should always match between online and offline. Something else that we also realize is that the features are only as fresh as the last write to the store. And if we are using sliding windows and writing every 30 seconds, if we don't get any events for a given IP or something like that, we stop writing into DynamoDB. Then what happens is that in the example that you are seeing there, the last write wrote 5 as let's say the count, but then we never update the value. So we end up with a stale feature because there's no more windows for that given entity. And in order to solve this, we introduced a TTL. So basically, every single row carries an expired at, which is basically going to expire the record once the record no longer makes any sense. And because we use DynamoDB, the AWS doesn't really ensure that the expired at is going to be, the record is going to be deleted right away. Sometimes it might take a few minutes or even a few hours. So we also look up, in the lookup layer, check whether the record was expired or not. And as a rule of thumb, we try to ensure that the TTL that comes with a row basically is higher than the slide interval. And the reason for this is that if it was lower, we would probably end up with null values in between windows. So if the TTL was 15 seconds, there's another 15 seconds until the next window, so we would end up with null values, which is not ideal. And probably the biggest learning for us was understanding where the freshness budget, or where we are actually spending the freshness. So the first thing that comes to mind is the slide interval. So if the windows are only sliding every 30 seconds, that's where we are spending most of the time. And that's true. But there's a lot of other things that actually come into play as well. One of them is the computation of the features themselves, which can take up to 3 seconds. Then the watermark, or how long we wait until we have, for late events. And last but not least, the thing that surprised us the most was actually publishing to DynamoDB. Because every 30 seconds we are publishing millions of rows to DynamoDB, this can actually take a while. And it becomes a compromise of the right capacity units that we provision on Dynamo and how fresh we want the features to be published. One thing that happened, for instance, in production was that the writes were queuing because we didn't have enough capacities provisioned in Dynamo, and we had no idea about that. So Dynamo was throttling, the writes were still ending up there, but we were losing a lot of freshness because of that. In order to solve this, we introduced basically monitors around every single step in the pipeline, and we now monitor the end-to-end freshness as well. And basically, like, it becomes, just like sliding windows, provisioning capacity in Dynamo becomes a compromise of costs and freshness. So we can provision really high write capacity units, but then we are spending a lot of money to ensure that the features are published rather quickly. Where did this get us? So after taking the model to production with sliding windows built on top of the new platform, we actually were able to identify 20% more fraud, which contributed to a 10 million more fraud identified every single year. And because our fraud models are not only used for fraud, but also other payment optimizations that actually, where we can ensure that the payment is accepted, we actually are looking at an 8-figure revenue opportunity for us, which was pretty cool. But this was sliding windows, and sliding windows can only get us so far. So the next step is to go under the second freshness to ensure that we are able to detect and act even faster than we are with sliding windows. And this is where Databricks helped us pushing for even more freshness.
Yes, so as we've covered, like, we're limited with the freshness to this model of the sliding windows. So if you're familiar with sliding windows in structured streaming, you can specify a time interval, and then the events as they arrive, they're bucketed into those time windows, and that time window slides by whatever time interval you want. So that's got some limitations on it. For example, if you get certain events, a pattern of events arriving, as we'll see on the next slide, then you might miss potentially a fraud event. Obviously, the benefit of sliding windows is that it's quite easy to have parity between your online and offline features, because it's easy, it's a very simple computation to compute the offline features, and then they'll match the online features. But the problem you've got is if you've got a very spiky, if someone's doing fraud attack in like a few seconds or something like that, and your slide window is maybe 30 seconds or something like that, then you could have a fraud event which is happening over the boundary of the slide, and therefore you miss actually that this fraud event is happening because half the fraud attacks happen in one window, and then by the time the window is moved on to the next slide, then the other events are in there. So you miss the action that's happening. So let's see how this looks in practice. So yeah, of course, so the guy who's doing the fraud isn't nicely planning his fraud attack so it all lands in one sliding window, and so you pick it. So there could be a scenario, particularly if the sliding windows, if the slide is quite large, where you miss a fraud attack or you fail to detect, because obviously you're measuring a threshold of distinct IP addresses or device fingerprints or whatever feature, whatever entity you're using. So you could miss that because the guy who's doing the fraud is not going to be so kind as to make sure all his attacks land in the same sliding window. So how do we avoid that? So the way to avoid that is to move to what we call session windows. So the idea with a session window is that as you see a new IP address, you effectively start the session, and then as you see new events arriving for that IP address, you're going to just grow the session. So that session is going to grow. Potentially, you might see the five payments within that window, as you can see, so 6 payments on the left-hand side. So you'd actually capture the attack burst in one session. And so in this case, the benefit here is you've captured the full extent of that fraud attack within one session. If there's then a gap, so if it was a normal payment, obviously you'd see a transaction, and then you'd see a gap, and then another transaction. So you can then expire that session because it doesn't look like fraud, it's normal behavior. But with the session windows, you're then going to capture that fraudulent activity within one session. So for those of you who are familiar with structured streaming, you'll probably know that there is a built-in session window. And so that offers some benefits, as we've talked about, over the sliding approach. So in the sliding approach, every payment event will go into its separate window, depending on how often you're sliding. So if you're sliding once every 30 seconds, so if you're sliding 30 seconds and you're moving the slide every 5 seconds, then that event is going to be in 6 buckets, because it's going to go in every time it slides, it's going to move into the next bucket until eventually it falls out of the window. So that creates a huge number of windows. So it's not very efficient either. So the advantage with the session-based approach is actually we manage that session window, and all those events effectively are handled together. So we're not exploding the state, which happens in the left-hand side, because each of those windows on the left-hand side is going to have to be stored and maintained in the state of Spark structured streaming. But there's a few downsides with the built-in session window, some quite major downsides. One is you don't get control over when events are emitted, because, of course, if you see a fraudulent transaction start to happen, a pattern of fraudulent events, you probably want to send an event as soon as you trigger the point that you think it's fraudulent. So say you get 5 transactions coming in, and maybe on the 5th one you go, OK, now we're going to alert, because this has passed the threshold of distinct transactions for this IP address. So now we're going to flag that, and we're going to write that to the feature store. But you can't do that with the built-in event. You have to wait for the session window to close. So that's a bit of a pain. Another problem with the session window is that you can only define it for one time period. So in this example, we want to have multiple time periods. We want to be looking back over 30 seconds, over 5 seconds, to see the amount of distinct events. Well, how many distinct transactions are there in the last 30 seconds? How many distinct transactions are there in the last 5 seconds? They become separate features in the feature store. So we want to be able to manage that ourselves within the state management. So how do we do that? So we use this feature called transformWithState. And this is an API that's been around for a while. It was originally called Apply with State in Pandas. There's been numerous iterations of it. And now it's kind of settled on this name of transformWithState. And what transformWithState allows you to do is fully customize how you handle new events arriving. So when you see a new transaction arriving in the input stream, you've got full control over what you do with that. And you've got full control over how the state is managed. So for example, you could maintain a list of, for a given IP address, you can maintain a list of the timestamps when that IP address has been used. Or you can do it, for example, for a given device, you can see how many IP addresses are being used for that device. So you've got full control over the state and how that works. And also you've got control over when you emit an event. So like I say, you can look at those scenarios where perhaps you see 5 transactions arriving. OK, that's tipped the threshold. We've seen 5 transactions in the period of 2 seconds or something like that. OK, so let's emit an event because we want to update the feature store. This looks like this is fraudulent. The downsides with this approach, there's always downsides. The downsides with this approach is we've now moved away from the very kind of comfortable sliding window approach, which made it easier to maintain our online and offline store. So we've got to think hard about how we calculate the offline store, because now the size of that session window is not fixed time boundaries. It's based on when the events arrived. And if we're doing like distinct counts over the period of 30 days or a year, so we're looking back potentially 30 days in transactions for a given IP address, then that's potentially a lot to calculate. So let's dive into transformWithState. So the benefits here, like I say, is it gives you full control over the state we store. So we can maintain that distinct list of timestamps used for a card, distinct list of IP addresses. We can also maintain a count of how many times we've seen transactions for this IP address. And it supports both event time and processing time timers, and that's quite important because we want to use the event time. So in this case, the event time is the timestamp the transaction happened. The processing time is when the event arrives. Obviously, if there's any lag in the data coming from our upstream system, like Kafka, for example, our pub subsystem, then the processing time is going to be inaccurate. So we want to use the event time to calculate, because you might see, if you see any lag in the stream, then that's going to potentially miss a fraudulent event, because the events might be strung out when actually when they really happened, the transaction time, they were actually close together. You get full control, like I say, of how you process the input rows, and also how you handle timers. So timers are quite important because we can use timers to say, for a given IP address, if nothing's happened for a period of time, we can then say, okay, we'll downgrade this. We no longer think this is a fraudulent transaction. Potentially, at that point, we can also say, because we've not seen any transactions for 30 seconds for this IP address, we can then fire an event off to say, now clear the value in the feature store, because we now no longer think this is a fraudulent IP address. And the same code can run in stream and in batch. Now, like I say, because the paradigm is no longer moving from sliding windows with fixed time intervals to like a session-based approach, it can be quite expensive to do it in batch because you have to replay the events in order. But the benefits are, as we can see, is we're more likely to capture those fraudulent events than we were with the sliding window-based approach. So here's some examples of the type of state you can store in transformWithState. So a value state is just a single counter. So in this case, in an example of the fraud use case, we'd store things like how potentially like some kind of velocity counter, like just a count of transactions that we've seen. Maybe the last time we saw, the first time we saw a transaction within this session. So you can kind of then create features which are based on like averages of how many transactions we're seeing per second, that kind of thing. For distinct counts, obviously we might want to count like how many devices we've seen for an IP address if the fraudster is is trying different devices for the same IP address or vice versa. Or we might want to see, often fraudulent behavior detects things like, do we see the geolocation moving around much faster than we'd see an actual customer moving around? For example, have they moved 100 miles between two transactions which are very close together? So you can do those kind of things. We can store in the list state and potentially also the map state, we can store that kind of information which allows us to compute every time a new event arrives. We compute, for example, things like what's the number of distinct devices. We can do things like geolocation, those kind of things. So it's very flexible in what state you can store. With the sliding windows and the built-in session window operator, you just don't have this flexibility over how you can store the state. So here's what happens when an event arrives. So the new event arrives, and we'll immediately look at that event, obviously decode it from Kafka, and then we make a decision based on that. We're going to update the state. So for example, if a row comes in, we're going to obviously log the timestamp because we want to keep a count of distinct events. We might want to store like the IP address or the device fingerprint for the card. And then we can do a count of distinct on the fly. As soon as that event happens, we can then make that decision over, is this fraudulent or not? And then we can fire off if we decide it's fraudulent, we can fire off an event, which we can then push into, in this case, DynamoDB. At the same time, when we see anytime we see a new event, we can decide what we're going to do about the timer. So if it's a new transaction, we might say, OK, we'll extend the timer. Or we might do some other behavior, like say, after a period of time, we want to check whether this record now needs to be evicted from session. So for example, if we set a timer to be 30 seconds in the future, then if there's no events for 30 seconds for that card fingerprint, we can then evict that record from state. So this is kind of the future real-time feature pipeline that we're trying to get towards. So end-to-end, events come in from Kafka. They're in protobuf, so we deserialize with them. And then we push them into transformWithState. And this is doing the processing at scale of all these events. And at the moment, they're being written to Dynamo, potentially, Delta first, then to Dynamo. As Dinis talks about, we're very soon going to be writing them direct to Dynamo, skipping that Delta offline step. And we're also exploring writing them to Lakebase. Like I say, you can use this same approach with offline features. Yes, there's potentially performance implications. There's a way you can optimize around that by chunking the data by looking at like the gaps in the data. So for a given IP address, there's no data for, say, 10 minutes. Then you can calculate the offline features more efficiently. If you try and obviously replay all the data historically through transformWithState, it's going to be very slow. So you have to be quite clever about how you do the offline features. But fortunately, it's the same API. So it is the same API that you use to compute both. OK. One thing we still need to do is, so Dinis talked about creating this DSL, which allows the data scientist to use like a common language for creating the features for the sliding windows. We need to take that DSL and apply it to this transformWithState approach as well. So the data scientist can use the same language for creating features driven off this sessionization-based approach. I'm going to skip that one. So another added bonus of using transformWithState is that it's supported in real-time mode. So what's real-time mode if you're not familiar with it? Well, essentially, historically, Spark structured streaming has always been based around this micro-batch-based approach, which effectively means you've got all these executors consuming data in stream in parallel, and then every so often they all have to stop, agree on where they're up to in the processing, and then start again, as you can see in the top diagram there. So they all, every so often, have to stop. And there's a few problems with that. Is the one, obviously, that every time it stops it adds latency, but also if there's any skew in the data, for example, for a given merchant or for a given card fingerprint or IP address, there's suddenly a lot more transactions than there would be for another one. Then you get skew, and one of these tasks can then hold up the other ones. So all the other ones are sat there waiting, which means you could miss a fraudulent event for one merchant. Because there's an extra 5x transactions for another merchant, actually, this approach is sat there chugging through all those transactions for this merchant while it's missing fraudulent events on the other one. So that's the top approach is very heavily, can be heavily affected by skew. With real-time mode, you don't have that problem because all the executors are free to basically consume these transaction events as fast as possible. And that means we can also get the latency down. So with structured streaming, as Dinis showed earlier on that Freshness slide, is that there's always this processing element. You've got the sliding windows of 30 seconds, and then you've got calculating the feature, which takes 1 or 2 seconds, and then writing it to Dynamo, which maybe takes 7 seconds. So with real-time mode, we can really compress the time it takes to calculate the events down to potentially like 100 or 200 milliseconds. And with sessionization, we're also compressing that sliding window, so that sliding window is now reduced. So with this approach, ideally, we can get the freshness down to, once we do the write to Dynamo, we can get this down to potentially under 5 seconds. And so this is where we're going. So the sliding windows is in production. and we're looking at implementing the sessionization features. And once we've got that stable, then we're doing the real-time mode. So that's where we're going in the future, and we've been working on these for the last few months to POC these. OK, thank you very much, everyone. I hope that was useful and interesting.